Hey, what's going on YouTube? Welcome to the second tutorial in our series on programming a render engine in C++ and Ncurses. So initially I wasn't actually going to make this tutorial, I was just going to write all the math libraries and copy and paste them into the project file so that you didn't actually have to watch me sit down and program them from scratch. But the reason I decided to do this is because I wanted to make the series comprehensive, and if I don't include a detailed math explanation, I don't think it would actually fit what I'm trying to accomplish. So in this tutorial we're going to go over what a vector is. The next one we'll go over quaternions, and then we'll go over matrices, and that'll pretty much be it for the math, and then we can actually start programming the render engine itself. So just to give you a quick brief description of what a vector is, let's go ahead and assume we have a 2D space set up, as you can see right here. If we go ahead and open this up, you can see that we can use a 2D coordinate, and this actually works for all dimensions: 3 dimensions, 4 dimensions, 5 dimensions, all the way through infinite dimensions. But as you can see, we can take the coordinate 6, 5, and then we can represent a point in space using that. The next way we can reuse a vector is actually as a direction. So if I open this up, you can see that it is a direction going from the 0, 0 coordinate through this point, and it can keep going infinitely in this direction. But by taking any vector point, it has this direction already stored. We're actually going to talk about the length as well. The length of the vector is basically the Euclidean distance from 0 to the point on the vector, or to the vector's point position. So in this case it would be, if you think of it as a right triangle, it's going to be from this point to this point, and then this point to this point, and then you just take x squared, y squared, square root of that, and that is effectively how you calculate the length of a vector as well. And then another function that you can perform on a vector is the normalization function. And what that'll do is it'll take this entire vector, it has length all the way through here, and it'll make it a length of 1. So the point would actually be here on this. And the way we can accomplish that is actually by taking each component of this vector, so 6, 5, and then by taking the length of this vector, you divide each of these components by the length. So you'd take 6 and then you divide it by the length of the vector, if that makes sense. So 6 divided by, I'm going to write this out. So 6 divided by the length, and then 5 divided by the length. Yeah, let's make that a little better. So then 5 divided by the length, and then what that'll do is it'll get you the coordinates for the normalized vector. The biggest thing about vector 2 that I'd like to go over is the dot product as well. What this will do is it'll actually allow you to do directional multiplication. You multiply the shared components of the vector, so you take a dot x times b dot x plus a dot y times b dot y. And then what you end up with is essentially it's kind of difficult to explain, I guess, the amount of A that's projected onto B. It's it's a little bit confusing, but what we're actually going to use this for is for getting the angle between vectors, and this will be useful in lighting calculations and for other various reasons. But if you get this angle right here, the way the dot product is defined is, as I've already mentioned, a dot x times b dot x plus a dot y times b dot y, but it has another component. It actually is equal to the length of a times the length of b times cosine theta. So by using that cosine theta operation, we can do the original thing and then take the inverse cosine to actually get the theta value of the vectors, and then you can use that to determine how close two vectors are to it being in the same direction. Of course you have to normalize them first, but we're definitely gonna find that very useful in the future. So let's go ahead and jump right into the code. So to start, let's go ahead and make include slash vector2.h, include slash vector3.h, include slash vector4.h, and then vector2.cpp, vector3.cpp, and vector4.cpp. So those are all made. Let's go ahead and vim include, well actually let's start with the make file. Here we're going to go down to deps and then start with vector2.h, vector3.h, and vector4.h, and then here vector2.o, vector3.o, and vector4.o. Let's open up main.cpp, make sure this builds it. Okay, now let's go ahead and open include slash vector2.h. We can add some include guards, if and def include vector2h, define include vector2h, and then end if class vector2. Alright, so we'll have this class set up with public and private, and we're going to need to include float x and y for vector2's because these are our x and y coordinates on the grid. Let's go ahead and make the constructor. We'll have default values for them as 0. So what we're going to want to start with is a normal constructor. We're going to want a copy constructor. So we'll get the copy constructor. We're going to want a operator equals as well. Vector2 reference is the return type for this. Call this vect. And then we also are going to want a destructor. I'm just going to put that inline actually. No reason. Actually, you know what? Let's implement it just to make sure that, just to keep compile times down. Okay. So first we're going to want a float function to get the length. And this will be const. So we'll have a const function to get the vector's length. Now let's also have static functions for the mathematical operations. The reason I'm doing this is because I don't want to do operator equals, because then I have to program operator plus equals, minus equals, and operator plus each separately, so I'm not really in the mood for that, and I think it'll take too much time. So let's just go ahead and say vector2, well actually static void add const vector2 reference left, const vector2 reference right, and then as the last parameter we need a vector2 reference dest, and then we also are going to need static void sub const vector2 reference left, const vector2 reference right, and then vector2 dest. So we have add subtract, and then we also want to add mul as well. We might not use this, but we'll have it. So we'll have mul in addition to those. There are also two other functions. If you remember, we had the dot product function. So static float dot const vector2 reference A, const vector2 reference B, and then we also want the distance. So static float dist const vector2 reference A, const vector2 reference B. So those functions will return, well, this one will return the dot product of the vectors, and this one will return the distance between the two vectors. And also let's have static float get angle, or actually let's just call this angle. Reference A, const vector2 reference B. Okay, so we'll have a function to get the angle between the two vectors. And if you remember, we'll just use the dot product for that. I'd also like a static function to return the normalized form of the vector. So static vector2 get normalized, and then we'll take in a const vector2 reference V. And then let's also have Actually, yeah, let's actually call it a day for that. Or so then we'll have void scale, float s, and then we're also going to have void normalize, and that'll make it a length 1 vector. And then also let's add some getters and setters. So inline void get x const return x, and then oops. So this will be get y, and then we will have to make sure to change that to y. So that's just an inline function to get the x and y values. Also, let's have inline void set x, not a const. Float x, this dot x equals x. And then also set y, taking float y, this dot y is equal to y. Alright. That should be everything for the implementation or the definitions part of this file. So let's vertical split into vector2.cpp, and then let's include we'll include from here vector2.h, and then let's start by implementing the constructor. Float y, and then actually let's go ahead and make this initialization list. So we'll initialize x with the x parameter and then y with the y parameter. And then we will go ahead and make the copy constructor. And then initialization list this, so x is v.x and y with v.y. Now let's make the operator equals. So vector2 reference vector2 operator equals const vector2 reference vect. And then this is real simple. X is equal to vect.x, y equals vect.y. Alright. So now we'll do the destructor. Don't need to actually do anything for this, but it's good to have, so we'll have it. Actually, I'm going to go ahead and make this destructor virtual. No particular reason, but may as well. Okay, so the next function we're going to implement is the length function. To do this, we're going to need to include math.h. So void length, well, to do this, we're going to return sqrt x times x plus y times y. And that's quite literally just the distance formula that you probably learned in elementary school or middle school. And it will return the length of the vector in a floating point value. Well, actually, not right now, it won't. Okay, now it will. Now we'll add void vector2 add, const vector2 reference left, const vector2 reference right, and vector2 reference dest. And it's actually going to be the same thing for the other two, so yj and 2p. Separate those, and then we need sub, add, and mul as the functions. So these are real simple. We're just going to do dest.x equals left.x minus right.x, and then dest.y equals left.y minus right.y. So paste that into here. So then add, we'll just switch this to an addition sign, and then multiply, we'll switch this to a multiplication. Okay, so we have those functions added. Now let's do the dot product. So float vector2 dot const vector2 reference left, const vector2 reference right. And the dot product is really easy. I talked about it in the other part of this video, but it's going to be return left.x times right.x plus left.y times right.y. So real simple right there. Now let's return the function, or make the function to get the angle. Okay, so the angle is going to be effectively inverse cosine of the dot product. But first we actually need to, well, we actually have to divide by the length of each of them. So to this we're going to return a cos. So actually let's start with float dot is equal to vector 2 dot left right. So we'll get the dot product between the two. And then we'll return dot divided by, well, a cos dot divided by left dot length multiplied by right dot length. And that should be able to return that would return the angle between the vectors in radians. Let's make sure we have our spacing how I like it. Okay. Now the distance is going to be real simple as well. So float vector 2 dist const vector 2 reference left, or a const vector 2 reference b. The distance, all you have to do is subtract the two vectors and then take the length of the vector. So we'll take vector 2 diff is equal to the difference is going to be equal to a minus b. So vector 2 sub a comma b. And then what we do is we return diff dot length. However, we can actually do this in a slightly faster way. So float x is equal to a dot x minus b dot x, and float y is equal to a dot y minus b dot y, and then we can return sqrt x times x plus y times y. So that's the same thing, but it's not going to be creating an object and then calling functions on the object. So I think that implementation is just a little better for this. So to get the normalized vector, we'll do vector 2 get normalized, and this will take a const vector 2 reference a and of course b. And then the normalization would be, to return the normalization, we'll do vector 2 vector 2 read, and then we will give it, actually wait a second, this doesn't take two parameters. So we'll pass in the input through the copy constructor and then return read, and then after calling read.normalize. So that will go ahead and normalize the vector and then return it. Let's go ahead and delete those. The next thing we want is scale. Float s. To do this, all we're going to do is x times equals s and y times equals s. And then the normalized function, which we're using here, we need to implement it, otherwise we're going to get some errors. So to normalize the vector, it's real simple. All we're going to have to do for this is get the float magnitude is equal to the length of the vector, and then we do x divide equals length and y divide equals length. So that will make the vector a unit vector, or of length 1. That's about it for this, I believe. Let's make sure this compiles. Okay, so we have a few errors. Okay, so first of all, I made these, I wasn't very smart, and I made these void. This is supposed to be float. Okay, and also I used the length word here. I called this mag, not length. Right dot length. I messed this up a bit. I need to do 2 parentheses, not 1. And then no declaration matches float vector 2 length. Okay, and we need to make our length function. It needs to be a constant function in the definition. So add our const to that. We have one more error still, or inline void get x. Wow. Make sure that the set x are void, the set x and y are void, and these return floats. My apologies there. Okay, we have one more error here. We have return acos. Okay, we actually need one more parenthesis, it looks like, in that area. So in angle, we have to go ahead and add one more parenthesis. There we go. And no return statement for operator equals. Let's go ahead and fix that as well. Return dereferentation of this. Okay. All those errors are now cleaned up. Hopefully you followed that and got all those changes on your side as well. We're going to go ahead and now modify include / vector3.h and also vector3.cpp. We're just going to do pretty much the same thing for vector3, except there are going to be some small changes that we have to make. So to do this, let's go ahead and first start by copying this. So we'll put that in. It's actually, why did I open this here? Okay. So in the H file, let's paste in this, and then modify this to a vector3 so the include guards still work. And now it's everywhere there's a, let's go ahead and change every instance of vector2 to vector3. All of those should be changed now. So we have vector3, 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 and yeah, everything's changed to a vector3. So now let's go ahead and make the minor changes to this. We need to change this to float z equals 0, of course. Let's see, inline void set z, float z, this z equals z, and then inline float get z, const return z. And then also let's go ahead and add this z member variable down to the bottom. So now we just added one more coordinate. We have x, y, and z instead of just x and y. So now let's go ahead and come over here and copy our implementation. So yg, paste it in here, and then let's do the same thing where we find every instance of vector2, replace it with vector3, and then let's go ahead and make the changes to this as well. So z, we'll pass in this, and then let's take in a float z as well. So make sure you're including this in the initialization list. And then down here, z, v.z should be added there as well. And then z equals vect.z. And then for the length function, all we have to do is do plus z times z. So this is a addition sign. Just zoom in to make sure that you can see this. And then for sub, let's do des.z equals left.z minus right.z. And then add des.z equals left.z plus right.z. And then multiply is going to be des.z equals left.z times right.z. So there's our multiplication. The dot product just needs to be modified ever so slightly, where we're going to do adding on left.z times right.z. And then our angle is actually going to be just fine as it is. We don't have to change that at all. And then our distance, we need float z equals a dot z minus b dot z. And then adding on to the end plus z times z. So that'll be the new x, y, and z. Yep, that'll be the distance between the two vectors. The normalized function doesn't need to change. The scale function needs to be changed to z times equals s. And then normalize is going to be z divided equals mag. And that should be all the changes to that. Let's go ahead and see if that works. Yeah, we're good. So that is the vector3 function. Let's just do this for zoom. And now the last thing we have to do is do the same thing for vector4. So, well, actually one other thing. We need to make one small change to this static void cross, because vector3s actually have the ability to have a cross product, which is going to be the pretty much the polar opposite of the dot product. It returns one of the vectors that is perpendicular to the other two, and the magnitude is also the area between the two vectors. What we're going to be using this for is getting things like perpendicular directions, and it'll be very useful. You'll see why, especially for backface calling. So let's go ahead and implement this with const vector3 reference left in, well, actually let's call this 1 const vector3 reference 2. That I'm only labeling them 1 and 2 because that's how I remember it. So let's come over here, and then up in this location under, let's do it under this area. Okay, so the cross product is gonna, you can think of it as, oh, actually I need one other thing, and we need a destination because it returns a vector3. So you can think of it as if you're setting des.x. To do this, you're going to need information from 1.x, or not .x. You're going to need information from 1.z and 1.y. So for the first instance, des.x, we're going to need to do 1.y times 2.z. Because we're using the x and z components. So if I come over here, I can do 1.x times 2.z minus 1.z times 2.x. So notice how I just inverted this. So it's 1.z here and 2.z here, and then 1.x here and 2.x on that location. But the order does matter, so be careful when implementing this. Well, actually, I did make one small mistake. I even said it. This needs to be y. So definitely make sure that you're getting the y components of this. You're setting x to the y in z. So 1.y times 2.z and 1.z, yeah. So for the y component, we're using 1.z and 2.x for the first initial values. So des.y is equal to 1.x times 2.y, no, times 2.z, I believe. 1.z, actually it's going to be 1.z times 2.x minus 1.x times 2.z. 1.z, 2.x, okay. Yep, that should be good. Des.z is equal to 1.x times 2.y minus 1.y times 2.x. Okay, and that is the cross product. It returns a vector that is effectively perpendicular to the other two. So that's it for the vector3. Okay, we got some errors. Vector3 is private within this context. Yeah, I did make this private, didn't I? Interesting. Because it is a static. Okay. Let's see if I made any other errors here. A lot. Vector2 cross has not been declared. It should be void. So we have vector3 reference 1, vector3 reference 2, and then the destination. What the? Oh, I think I know what the problem is. Never mind. Oh, yes, I do. Okay. I might edit that out, but if I didn't, then that's fine. Okay, that was the error. It's not vector 2 cross, it's vector 3 cross. Okay. Alright. So let's go ahead and include vector 4. 4.h, and then vertical split with vector 4.cpp. So in the h file, once again, I'm actually going to copy from vector 2. So from the h file, we'll paste that in, and then replace this with 4. And then, of course, do our replace. So that'll replace it all with vector 4s. Our quick change we need to do here, change this to float z equals 0 and float w equals 0, of course. And then we need to add on our get z and get w. And then, of course, make this return z and this return w. And then same with this area. Set z, set w, float z, float w. And then z is equal to z and w is equal to w. And then, of course, we add in our private variables z and w. And that should be it for that. So we'll go over here. And then we'll copy and paste this into this section. Actually, I wanted to copy from vector 2. Okay, so from vector 2, we're copying that information from there. We'll instead now just do %s/vector2 vector 4g. So we replace that all there. And of course, we need to make this change. Float z, float w, and then add them to the initialization list. And then add this to the initialization list. And then we also want to do z equals vec.z and w equals vec.w. We'll make our changes to the length function, which will be plus z times z plus w times w. Our sub des.z equals left.z minus right.z, des.w equals left.w minus right.w. And then des.z equals left.y plus right.y. Well, not y, z. I don't know what I'm thinking. Des.w equals left.w plus right.w. And then multiply, of course. And then des.w equals left.w times right.w. Alright. So the dot product will just make a simple change here. Plus left.z times right.z. Plus left.w times right.w. So that will be the changes for the dot product. The angle stays the same. Actually, let's not even include the angle for vector 4s. So we'll delete that from the h file there. Vector 4s, there's no reason to really get the angle between vectors. There's barely a reason to do it for vector 3s, but there is a reason, so we'll leave it. Float z equals a dot z minus b dot z, and then float w equals a dot w minus b dot w. And then we will return this with plus z times z plus w times w. And also, scale is going to be z times equals s and w times equals s. The normalization stays the same, and then for the normalization we do z divided equals mag and w divided equals mag. Alright, so that is all the changes to all the changes that we made for this. We just added simple vector math functions. Next tutorial, we're going to go over the quaternions, and then after that, the matrices. And then from there, we'll be able to jump into frame buffers and probably start actually building the render engine. So I'll see you all next time.